Hello. So in this lecture, we're going to start our discussion of divide and conquer algorithms. The basic idea in divide and conquer is that we break the problem into subproblems that are the same versions of the same problem, and we can solve those independently. We then typically recursively solve those subproblems. By that, I mean, we take one of those subproblems and we further break it into more even smaller subproblems and so on until we get all the way down to like a base case, and then we come back up. And to come back up, we appropriately combine the answers of each of the subproblems. So I'm going to go through several examples of how this kind of idea works that will then, I think, make it a lot clearer what we're talking about. And to begin, let's look at multiplication again. So let's say we want to multiply two n-bit numbers, x and y. And for right now, because it makes the notation easier, let's assume that n, the number of bits, is a power of 2. So how do we solve this in a divide and conquer fashion? The idea is that we're going to split x and y into two pieces, their left half and their right half. Each is an n/2 bit long number. So it looks like this. We write x as a left part and a right part. And similarly, we write y as a left part and a right part. And so the left part is just the bits that appear first. Let's say if it's an 8-bit number, these are the 4 bits that appear first, and then these are the next 4 bits. And so the overall number is going to look like 2 to the power of n/2 x left plus x right. Y left plus y right, where this right here is a bit shift by n/2 bits. And so that's what I've written here as well. X can be written as the rightmost n/2 bits, or the leftmost n/2 bits shifted over, plus the rightmost n/2 bits. And each of these numbers, x left and x right, are n/2 bits long. So let me just give you an example. Let's say that x is the binary number 1 0 0 1 1 1 0 0. Then I call these 4 bits x left and these 4 bits x right. So this is x left, this is x right. So in other words, x left is just the 4-bit number 1001, and x right is the right, and then x can be written as 1001 times 2 to the power of 4 plus 1100, which equals 1001 bit shifted by 4 bits plus 1100, which is just 1001 1100. Okay. And now, why am I doing this? Well, the reason is that now to multiply x and y, I could instead multiply the right-hand side of x here, this x left, x right thing, by the y left, y right thing. And so that's this here, right? X times y can, just plugging in their definitions, can be written as 2 to the power of n/2 times x left plus x right, multiplying the same thing for y. And when I expand this out, I get an x to the power of n times x left, y left, plus 2 to the n over 2. And then I get this, the cross terms, right? X left times y right plus x right times y left. And then I finally get the x right times y right term. Right? This middle one is the x left times y right plus the x right times y left terms. And so you can see then, instead of multiplying, this on the left-hand side is 2 n-bit numbers. And each of these are n over 2 bit multiplications. Right, so instead of doing 1 n-bit multiplication, I could do 4 n over 2-bit multiplications along with some bit shifts. And so that's exactly what I'm saying here. Therefore, to multiply 2 n-bit numbers, x times y, we can instead multiply 4 pairs of n over 2-bit numbers, x left times y left, x left times y right, x right times y left, and x right times y right. Then we combine with 3 additions, 1, 2, 3, and 2 bit shifts. So what's the runtime of this? Well, the idea is we write down, let t of n be the runtime on n-bit numbers. Then we can see that to compute t of n, we've performed 4 multiplications of n over 2-bit numbers. Plus so I do these 4 multiplications, which is 4 times the time to do n over 2-bit multiplications, and then plus the time for addition. Addition is big O of n, and then bit shifting. So this overall thing is big O of n, where what we have here, this is time for 4 n over 2-bit multiplications. And this is time for 3 additions and the bit shifts. Now, we're going to shortly go through a method for solving these recursive equations. But for right now, I'll just give you the answer. And the answer is that, so we'll shortly see how to solve this recursive equation, but for right now, the runtime of this comes out to be, when I solve this recursive equation, is order big O n squared. And so, okay, this is maybe a little bit disappointing because we went through all this work. It looked like we were going to do something kind of cool, and then we just got the same runtime as the algorithm we already had, which was the multiply algorithm from the previous chapter. However, we're actually onto something here, and we can do this a little bit better. So can we do something smarter? And the answer is yes, and it relies on a kind of cool trick, which is, what if instead of computing these 4 multiplications, what if I only compute 3? I compute x left times y left. That's this one up here, or sorry, that's I think I have a typo up here, right? This, apologies. This should say x left times y left, x left times y right, x right times y left, and x right times y right. Those are the 4 multiplications. So instead, I'm going to compute x left times y left, this one. I'm going to compute x right times y right, this one. And then I'm going to compute this thing. And my claim is that if I compute this, I can recover this middle term. So what I do is notice that then the term I want, which is x left, y right plus x right, y left, right? That's the term I need here. It can be computed from these as x left plus x right, y left plus y right, minus x left, y left, minus x right, y right. And so this here is what we need or what we want. And these are all things that we have. And the other thing you notice, right? So these are each n/2 bit numbers, x left times y left and x right times y right. This one here, note x left plus x right is not x. What it is, right? If we go back up to this example, it's what you get when you add 1001 and 1100. It's at most an n/2 plus 1 bit number, right? You have to first, to recover x, you have to bit shift x left by 4 bits or by n/2 bits. So this also is just it's an n/2 plus 1 bit multiplication, which is big O of n/2. Well, so this now means that what we're able to do is to solve a problem of size n, we instead do 3 n/2 bit multiplications. Like I said, this is actually n/2 plus 1 bits, but that doesn't really matter. Plus the time to combine them, big O of n. So that's the time to compute x left plus x right. That's an addition. To compute y left plus y right, that's another addition. And then to do this, I need to do 2 subtractions. And then I have to do 2 bit shifts, and then I have to do 2 more additions. So now there's more stuff going on in this big O of n, but it's still big O of n because there's still just a constant number of big O n operations. So we get, this is now 3 n/2 bit multiplications. And then this is time for, we have 4 additions, 2 subtractions, and 2 bit shifts. And if I solve this recursive equation, it now gives us T of n is big O of n to the power of 1.59. And that's kind of cool, right? We went from now our previous algorithm, the one in the previous chapter, was n squared. This idea where we used 4 multiplications also gave us n squared. But now we found this trick where we could just do 3 different multiplications and recover the middle term by taking this minus this one minus this one. And we get the runtime down to n to the 1.59, which actually for large n gets significantly faster. So I can write out this function more precisely. And this is just implementing the code, but now I'm just, what I've written so far, notice the reason I said n was a power of 2 is then I can just nicely write n/2, and that I know that's an integer. And similarly here, when I do, when I write a bit shift of 2 to the n/2, that's again an integer. So that makes sense to bit shift by that. If n's not a power of 2, then I have to take floors and ceilings, right? To make sure I'm getting integer values. So here we fix that. And the divide and conquer algorithm looks like this. So we called it mult, divide and conquer, takes in x and y, and it outputs x times y. If n is 1, if the integers are both 1-bit numbers, then we just return their product. Otherwise, we define x left to be the ceiling of n/2, the leftmost ceiling n/2 bits, and x right to be the remaining ones, which will be the floor of n/2 bits, the rightmost. And then we do the same thing with y left. Then we compute those those three different products, x left times y left, x right times y right, and then x left plus x right times y left plus y right. And then we just implement this same, this is just the implementation of this expression here, where now I've just fixed these bit shifts for the case when n is not a power of 2. So the 2 to the power of n and the 2 to the power of n over 2. They become 2 to the power of 2 multiplying the floor of n over 2. And this one becomes 2 to the power of the floor of n over 2. That's the right bit shifting given these definitions of x left and x right. Okay. So you can see this is a recursive algorithm. It calls itself 3 times within itself, and then it performs all of these operations. This set of operations. So it's 3 calls to itself. In those calls, the input has halved in size, and then order n time to compute all this from the results. So the divide and conquer tree that we're creating, if I want to give you a bit of a better understanding, is how do I get n to the power of 1.59? Like what's going on there? Let's look at this divide and conquer tree. So at the top, let's say I'm multiplying 2 8-bit numbers. So I have an 8-bit number multiplying an 8-bit number. To do that, I break it into 3 4-bit multiplications. So 4-bit times 4-bit. That's say for x left times y left. Another one. And then another one over here. And then again, to multiply these, I do 3 2-bit multiplications. So this is going to be, I'll just write 2-bit times 2-bit. I think you get the idea, but I'm just writing them all out. And then each one of these recurses one more time makes 3 1-bit. Like this. And so you can see this tree is expanding as we go down. And from this tree, we can kind of determine the runtime. So the first thing is how many levels are in this tree. If we start off with an n-bit number, then the next level is n over 2. The next level is n over 4-bit numbers, right? And we go down until we get down to 1-bit numbers. So the tree has log base 2 of n levels. In the kth level, how many multiplications do we have? So let's say this here is level 0. This is level 1. This is level 2, and so on. Then in the 0th level, we have 1 multiplication. In the first level, we have 3. In the next one, we have 9, right? Which is, so this 3, 9 is 3 squared. And level 3 is going to be 3 cubed, right? So we have, in the kth level, we have 3 to the k multiplications. That means that in the bottom level, we have has 3 to the power of log base 2 of n multiplications. right? In this case, the log base 2 of 8 is 3. So we get 3 to the power of 3 multiplications in the bottom level, which is 27, right? And that's exactly what you're going to get, because each one of these 9 nodes has 3 children. 9 times 3 is 27. Now, recall, I'll write this in a different color. Recall the change of base. So the change of base for log, which tells us that log base b of x can be changed to a different base a as log base a of x divided by log base a of b. Also, log base a, or how about I write it like this? Log base b of a equals 1 over log base a of b. And so from that, from those two tricks, I have these 3, if I want to simplify this 3 to the power of log base 2n, I can rewrite it as 3 to the power of log base 2 of n. Let's change the base to 3. Then I get 3 to the power of log base 3 of n divided by log base 3 of 2. Which equals, I'm going to get 3. So now I get 3 to the power of log base 3 of n, all to the power of log base 2 of 3, right? I used this second rule to bring log base 3 of 2 into the numerator, and then it becomes log base 2 of 3. And I've just now grouped these two things. So this first thing is n to the power of log base 2 of 3. And this is n to the power of 1.59. And so you can see in this particular case, for this particular recursion tree, all the work really is done at this bottom level. The algorithm recurses down to the very bottom level where we have 27 one-bit multiplications. Then you combine their answers going back up the tree, and basically all the work is done down here. And the 1.59 work is done down there, and then that actually matches the overall runtime of the algorithm. There are other cases, depending on the value, like the way this recursion looks, that instead the work is like equally spread across the entire tree, or there's even cases where the majority of the work is done at the top of the tree. And this is what leads into what's called the master theorem, which is how we solve recursions of this type. We'll get ones where all the work's done at the bottom. We'll get ones where all the work is kind of spread equally across the tree. And we'll get ones where all the work is basically done at the top. This is an example where it's all done at the bottom and we get the runtime that we had above. So let's now go over recurrence relations. So for a divide and conquer algorithm, I'm going to now generalize this idea of writing this recurrence relation. So we solve a problem of size n, but by dividing it into a subproblems of size n over b, and then combining their answers in big O n to the d time. So these A, B, and D are the things that characterize the particular algorithm we're using. The overall recurrence looks like Tn is equal to A Tn over B problems, right? A problems of size n over b plus big O n to the d time to combine their answers. And the master theorem tells us the solution to this recurrence relation. And it says if we have these constants A, B, and D, then the overall runtime looks like one of the following. It's big O n to the d if d is greater than log base b of a. It's n to the d log n if d is identically equal to log base b of a, and it's n to the power of log base b a if d is less than log base b of a. If you go back, if you now match a, b, and d back to this one here, so a is 3, b is 2, d is 1, and you see which case are we in, here, you'll find that we're in this third case where d is less than log base b of a. And so the runtime is exactly this big O n to the power of log base b of a, which is n to the power of log base 2 of 3, right? Which gives us this 1.59. But let's now understand, how do we get this recursion relation? And this is the last part of this lecture today. And so this proof will take a little bit of time to go through. So to simplify the proof, just to make it a bit easier for the notation, I'm going to assume that n is a power of b. So to simplify notation, this will get the idea across still, and then I don't have to worry about getting the floors and ceilings of n over b correct. So just following our argument above, we know that the size of the subproblems decrease by a factor of b at each level. And so therefore we reach the base case in log base b of n levels. This is the height of the divide and conquer tree. The other part is the branching factor, right? When we wrote out this tree up, let me scroll up here, right? Number of levels, that in this case, it was log base 2 of n, because b in this case was 2, right? Here it was a 2. In general, when it's a b, then it's log base b of n. And then the branching factor here is how many new subproblems does each one create? Here it was 3, right? In general, it's a when we have a recursion of this form. We get a problems of size n over b. And so the branching factor is a. That means that the kth level of tree has a to the power of k subproblems. It was 3 to the k in the example above. And each problem in that level has size n over b to the power of k. So the total work at level k is the following expression. We have a to the k problems. Each one is size n over b to the k, right? And the work that we actually do at a level is the work in combining. Like, let me just go back up to show you what I mean. Go back up to here. In a given level, we're calling this function, right? It does two things in the function. One is all the stuff outside of the recursive calls, and the other is the recursive calls. So the work done at this level, like in this function itself, not including its further recursive calls, is just the work done in lines 1, 2, 3, 4, and 8. So that's the time for all these additions and everything. And so that is this big O n to the d, right? But now in this level, the problems aren't of size n, they're instead of size n over b to the power of k. So we get the work we do in that level is big O of n over b to the k, all to the power of d. And so let me just rearrange this, because I want to get the stuff that depends on k separated from the stuff that doesn't depend on k. And so I can write this as big O n to the d multiplying a over b to the d all to the power of k. And so this here is the number of subproblems. And this here is time to combine their answers. And so then now I want to sum up the work. This is the amount of work I do in the kth level of the tree. So the total amount of work I do in the entire tree is just going to be summing this up over all k, right? Over all the log base b of n levels in the tree. So thus the total work is t to the n, or t of n, which is the sum over all the layers of the tree. So k equals 0 up to log base b of n of this thing, which is big O n to the d multiplying a over b to the d all to the power of k. I can factor out the big O n to the d part, and then I'm left with this sum. So this big O n to the d is just something that's out in front. And what we have to figure out now is, what is this sum? Right, so let's look at this sum. And let's also let L be equal to log base b of n, right? Just so I don't have to write log base b of n. So the sum is the sum from k equals 0 to L of a over b to the d all to the power of k. And I can rewrite that as the sum, oops. Sorry, I'm having trouble writing a sum for some reason. The sum from k equals 0 to L of c to the power of k, where c is equal to a over b to the power of d. And if you look at this sum, it looks like a actually a geometric series. And so if you recall, or like just search online to find the geometric series, we get that the sum from k equals 0 to L of c to the power of k is equal to 1 minus c to the power of L plus 1 over 1 minus c, as long as c is not equal to 1. Now, there's 3 cases for us to consider for this sum, and it's going to depend on whether or not this geometric series, it's really useful for the case where c is less than 1. then we get the following result. In the case when C is greater than 1, then this is just a polynomial, right? And then it's dominated by its highest order term. So we're going to get 3 cases. Let me go through them. So we have case 1 is that C is greater than 1. That then means that A over B to the power of D is greater than 1, which if I take the log, right, bring B to the power of D onto the right-hand side and take the log, what it's telling me is that the log base B of A is greater than D. In this case, this expression here is just C to the 0 plus C to the 1 plus C to the power of L. In the case where C is greater than 1, this sum is dominated by the last term, C to the power of L. So in this case, sum is dominated by the C to the L term, the highest order term. And so the sum equals big O C to the L, right? Which is just plugging in what C is. It's A over B to the power of D, and then plugging in what L is. L is log base B of N. Log base B of N. This then equals big O of, I get A to the power of log base B of N divided by, in the bottom, I get B to the power of D multiplying log base B of N. When I simplify that, that's just N to the power of D. And then if I look, right, this is the sum. That's this term here. That sum multiplies big O N to the D. So the big O N to the D here cancels out the N to the D in the denominator. And therefore, in this case 1, I get T of N equals big O A to the power of log base B of N. And that holds in this case where log base B of A is greater than D. Okay, that's case 1. Case 2 is that C equals 1. In this case, we have that D is then equal to log base B of A, right? Because we have A over B to the D is equal to 1. And so D equals log base B of A. The sum then, this sum is just going to be 1 to the power of 0 plus 1 to the power of 1 plus 1 to the power of L, right? It's just going to be the sum equals the sum from K equals 0 up to L of I. Oh, sorry, of 1, which is just L plus 1 terms. Plugging in the value of L, that's log base B of N plus 1. And so in this case, I get that T of N is equal to big O N to the D multiplying big O of log base B of N, right? Log base B of N plus 1 is just big O of log base B of N. Because this is a constant and this term grows with N. And so this just equals big O n to the d log of n. One thing you'll notice is that I've dropped the subscript b here. That's actually on purpose, because the whole point is if we go back up to our change of base here, we see that changing the base in the log only changes things by a constant. And so actually, if I just write log, not even specifying the base, it's not losing anything when it's inside a big O, because the actual base only modifies things by a constant, which just gets absorbed into the big O. Now, finally, case 3 is that C is less than 1. So in this case, A over B to the D is less than 1, which corresponds to log base B of A being less than D. Here, this sum now, C is a number that's less than 1. And so this overall sum now is big O of 1. Right? In the numerator, we just get 1 minus C to the power of something, which is a number less than 1. So this will be like, 0.5 on the top or something. And then in the denominator, again, we get 1 minus some number that's less than 1. So this is just a constant. So sum is big O of 1. And therefore, in this case, we have that T of n is equal to big O of n to the power of D multiplying the value of the sum, which is big O of 1, which just is big O n to the D. And that's in the case of log base B of A is less than D. Right? And the second case here was where if D equals log base B of A. And so if you match our three, so our second result is here. And then our third result is here. And these three match exactly our expression up here. And so if you think about what's happening in each one of these cases, in this case, this first case, we're doing basically all the work. Let's go. First case, we're doing all the work at the bottom level of the tree. In the second case, where C is 1, the work is equally spread out across the entire tree. And then in the last case, we do all the work at the top of the tree. And so it's big O n to the D, because basically that final combination of all the results you've got below, that's what eats up the most time. And so it's just the n to the power of D. And so now with this, basically, we have a result where to analyze a divide and conquer algorithm, we come up with a recurrence relation, and then we solve it using the master theorem. And so that's what we're going to do next class. We'll go through several different examples, starting with merge sort, but that's the end of this one. And thanks for listening. I'll see you in the next lecture. Okay, bye.